good afternoon and welcome. And we're going to start right away. I know our speaker needs to get out of town before it starts snowing. So the Cornell Climate Change Seminar is a long-running seminar series. We usually have about 13 seminars each spring, and it's designed to draw from many perspectives and disciplines on the critical issues of climate change. So today is a really great privilege to join the 2030 Forum for their inaugural talk with Stephen Pacala. And so I'd like to introduce Ben Furness to you, and he will introduce to you the 2030 project and today's speaker.
Good afternoon, everyone. Thank you so much, Peter. My name is Ben Furness, and as Peter mentioned, I currently serve as the Executive Director of the 2030 Project, a Cornell climate initiative. The 2030 Project, our mission is simple. We're looking to mobilize the Cornell community to support ambitious action on climate in this decisive decade. And Peter, the Climate Change Seminar Series is such a good demonstration of how Cornell is leading in this area and how we infuse our work with a sense of purpose and impact connected to a broader international community of scholars and practitioners all working to take on this big challenge. And I'm so pleased we could celebrate this event today as the first partnership with the 2030 Project here on campus. Science and work at leading research universities is a central component to helping to support and catalyze ambitious decarbonization goals from governments, from corporations, from investors, and from organizations all around the world. And the work of our guest speaker today, Professor Stephen Pacala and his colleagues, really stands out as an example of the comprehensive, rigorous, and relevant assessments that help to underpin our optimism that getting to net zero and a safer and more livable climate is not just possible, but appealing. Stephen Pacala is Princeton's Frederick D. Petrie Professor in Ecology and Evolutionary Biology and an Associated Faculty Director at the High Meadows Environmental Institute. And he was recently appointed to President Biden's Council of Advisors on Science and Technology, PCAST, in September of 2021. Professor Pacala has chaired 3 expert committees for the National Academies of Sciences, Engineering, and Medicine related to renewable energy, carbon emissions and mitigation, and the transition to a net zero economy. And that is what we're talking about today. He recently led the committee that released a National Academies report in February that provided a technical blueprint and policy manual for a wholesale transformation of the American economy to net zero greenhouse gas emissions by 2050, all rooted in the Princeton Net Zero America project. Pacala joined the Princeton faculty in 1992, has received numerous honors, I have a whole list here. It's really impressive, including the 2019 Weldon Memorial Prize from Oxford University, the 2013 Presidential Award from the American Society of Naturalists, an appointment as a lifetime fellow of the Ecological Society of America, and the 2010 Robert H. MacArthur Award from the Ecological Society of America. He has been elected as a member of the National Academy of Sciences, the National Association for the Advancement of Science, and the American Academy of Arts and Sciences. Please help me welcome Professor Stephen Pacala.
It's always a pleasure to be here at Cornell. My mic on here? Yeah, good. I've spoken here a whole bunch of times, going back over a period of over 30 years. Today, I want to give you a synopsis of where we are, primarily in the United States, with our plans to decarbonize the US economy. And the message is going to be that the situation is currently dire. It is dire politically, and we're about ready to blow a chance that's unlikely to come back again until those of you who are undergraduates are in your late 20s, something like that. And so if ever there's a time when you think it's good to write your congressperson, your senator, your member of the House, now is the time to do it. So I'm going to give you a little bit of a synopsis all at once. If you're in the energy business, you'll know a lot of this stuff, but some of it will be new. And if you're not, it'll be an introduction. All right, so I'm going to talk about, first is just a history lesson, why it is that all of a sudden, for those of you who are undergraduates, when you were in high school, you started to hear about the transition to a net zero energy system, why all of a sudden that happened, why that became the thing. And then I want to show you some recommendations from a policy manual for a fair, just, and feasible and economically feasible transition to net zero from the US National Academies of Sciences, Engineering, and Medicine. I'm going to give you some examples from this thing called the Princeton Net Zero America Project. And then I want to talk about the current lack of progress within the US Congress and implications for the invasion of Iraq. So I want to bring us to the present and talk about where we are and what's at stake and why this is the issue that is politically salient right around this pivotal notion that this is about decarbonization, net zero in 2050, and the path that we need to put the nation and world on over the next 10 years to get there, right? All right, so 1 billion years ago, but actually only 18, I wrote a paper with a guy named Rob Pacala that was cited a whole bunch of times. And what we did was to say, this was the trajectory of emissions. This is in billions of tons of carbon emitted per year, not billions of tons of CO2. To convert this into units we use nowadays, you multiply by 44/12. And if you don't know why 44/12, you should look it up. And what we did was extended the historical trajectory as a straight line, and then said, let's suppose we were just to freeze emissions at the then 2004 levels for 50 years and decrease them after that. Would that be possible with today's technology? Now, the reason we did this is that we wanted it to be feasible, to drop out these this green triangle of future emissions. And having inventoried the technologies that were available, we knew that it was feasible. It was currently the fashion in the second Bush administration for the Secretary of Energy to say that we lacked the tools to get started on an energy transition, and that's why they weren't doing anything. And we wanted to make the scientific case that that in fact was false. So saw him later and he said, you wrecked my speech, so that worked. In any case, the thing is that if you look at if you look at a current net zero trajectory, where we're starting about here, it's to go all the way to zero right there, all right? Now see how much more stringent that is. This is just getting started. And it was considered radical at the time, only 18 years ago. This was considered like radical. How could we possibly do this? The big surprise, the reason it was cited 3,000 times and was in Science and everything was because everybody was so surprised that it was feasible to do that much. And now all of a sudden, we're talking about that, which is just way more radical. We didn't do more back then because we didn't have the technology to do anything else. So what changed? Now, I want to emphasize also, before I say what changed, that this net zero by 2050 is the same thing approximately as 1.5 degrees of warming, okay? Globally net zero by 2050. If humanity isn't emitting anything, we'll reach a maximum of about 1.5 degrees Celsius of warming for the global mean. These are 4 different scenarios, emission scenarios from the IPCC's 1.5 degree report. Any one of these emission scenarios gets you to squeak under 1.5 degrees, and every single one of them reaches net zero emissions where the line crosses zero at around 2050. So 2050 and 1.5 degrees are interchangeable. And you might ask, well, which one came first, right? Did we know that 1.5 degrees was what we wanted? Or did we know that net zero in 2050 was feasible and then the other one came along? What actually happened? And a lot of people think that the science of consequences got better and more dire. That all of a sudden we discovered that we were staring down the barrel of a cannon that might go off at any minute, that the tipping points were somehow closer. And I don't want to overemphasize this, but the science of the tipping points, however discouraging, did not get significantly more dire through the period. We know a little bit more about instability of ice sheets than we did in the past. We know a little bit more about some of the some of the other tipping points, but it's a little slide of tipping points. I think of tipping points as monsters behind the door. They're the monsters. They're in your closet, in your bedroom at night, but these are really going to jump out and get you. And so these are, rapid deglaciation and loss of coastal cities, mass extinction, deep sea circulation stops, tropical famine because it's gotten too hot in the tropics. This is parts per million of CO2. We're at about here. And these are degrees of warming that are associated. The tipping points are thought to happen up here. All right, most of the tipping points are thought to happen up here. They're telegraphing their punches. The deep sea circulation has slowed, measurably slowed. The rapid deglaciation, we're seeing more rapid deglaciation. We think it's possible to get a meter of sea level rise from this now in a century instead of in a millennium, but it's still going to take millennia to get the multiple meters, we think. And so it's not really the case that 1.5 degrees is near a tipping point, at least so far as the science knows. It doesn't mean that the precautionary principle might want to say it's really a good idea to stop well before the world falls apart. But my point is that the science doesn't know that we're standing on the brink of a precipice. We're about to fall off. So why did the goalposts move? My thesis is that they moved because it became feasible to move them. We knew already that excess CO2 in the atmosphere was dangerous. What we also knew was that it was expensive to stop its growth, and all of a sudden, stopping its growth became far, far cheaper. And because it became far, far cheaper, it became a better sort of cost-benefit decision to bring the target forward where you're stopping emitting. And the point is that when you can think of this as a horse race. So let's start in 1990. We're going to look at the beginning of the race when the IPCC first sort of, the consensus report in 1990 really sort of framed the need to go all the way to net zero in stark terms for the first time. And so I like to think of this as a start of a horse race in 1990, a back straight around now, 2020, and a finish in around 2050. And when the race started, this was a sort of technological situation. Afforestation and reforestation were a thing, right? We knew that we could do that, at least in principle. Nuclear energy, it was the heyday of nuclear electricity. France was just starting its huge nuclear push, so nuclear was a big deal. Biofuels were all the rage. It was the year in which corn ethanol, which turned out to be not such a good thing, got entrenched. Wind and solar were present, but amazingly expensive. We'll show how much later. Hydrogen, which is all the rage now, was talked about then. And the bloom came off that rose for about 3 decades, but hydrogen was very expensive. Avoided deforestation. Everybody knew that was a good idea. Stop chopping down the tropical rainforest and emitting. And any engineer will tell you, you can always squeeze more efficiency out of a system and save money doing it. So these were the contenders. And basically they're around, there are candidates for, electric power if you want to go full nuclear, but there are problems with going full nuclear, right? And there really isn't anything for transport there other than biofuels. And there's limited biofuels feedstocks that you can produce if you want to grow crops for a living. But non-emitting energy sources were either the limited then by like hydro, or they were real expensive. And here's the important thing. The US government was acting like a venture capitalist firm in energy with a 40-year time horizon rather than a 10-year time horizon. And they were subsidizing everything. They were subsidizing fossil, they were subsidizing coal, they were subsidizing nuclear, they subsidized unconventional gas and oil, which led to fracking. They subsidized wind, they subsidized solar, they subsidized tidal, they subsidized this gigantic array of technologies and created little markets where firms could start and compete on price for the small subsidized market. And that drove costs down. It was a worldwide cooperation. It drove costs down in some, but not in all. And there were 3 distinct winners. First of all, wind and solar were just amazing winners. So back here in the in the mid 1970s, solar was over $100 a watt. There in 2015 at 61 cents, and now it's about 30. That buy down happened because manufacturers were competing with one another in this subsidized market. Until now, solar and wind did the same thing, are the cheapest forms of electricity on the margin of any altogether. And that's because subsidies, which are sort of a liberal solution, works with market competition, which is a conservative policy solution to drive costs down. And the fact that you subsidized everything means all you had to do was pick the winners. Now, the biggest winners for the renewable side were, even in the last 10 years, solar declined in price by 90%, wind by 70%, and lithium-ion batteries by 85% for electric transportation. Also, unconventional gas, whether or not this is fracked gas, whether or not you're for it or against it, it also decreased. That was another one of the winners of this sort of subsidy game. So that's the story. If we were talking 10 years ago and solar cost 10 times more, nobody would be talking about going to net zero because it'd be way too expensive. Costs came down by a factor of 10, all right? And that's what makes this feasible. So now we're on the back stretch in the horse race, and we've got wind and solar that are in the front. Avoided deforestation is still a deal. Transport batteries surged out of cell phones and into electric cars and allow you all of a sudden to decarbonize the vehicle fleet with renewable electricity. These two are so inexpensive now that they're almost happening anyway. The purpose of policy is just to speed them a little bit. Gas power with carbon capture and storage is a thing. It's more expensive than either of these two, but it's a way to provide baseload power that would work. Nuclear is still a thing. Efficiency will always be a thing. And then land-based negative emissions like forestry practices that store carbon. So this is the portfolio now, and what has fundamentally changed are these here. The main technologies that allow you to produce electricity and to drive your vehicle fleet with the electricity that you've produced without any carbon emissions cheaply, cheaper than the fossil alternative. That's the thing that fundamentally changed the equation. And it was because of a long history of international subsidies. When we faltered, Germany picked up the pace. When they faltered, China picked up the pace. Everybody in the world contributed to this and kept those markets alive until the costs benefited us all. The return on investment in the American economy is just really difficult to calculate. It's so large. It's worth on the order of the size of the economy itself. So really cool thing. So now with that portfolio, how do we do a transition to net zero? And this group that I'm head of that I chair for the National Academies of Science, Engineering, and Medicine is charged, and it's half social scientists, not just with technically, what do you not need to do? What policies are the best ones to put in place? But also, how do you do it in a way that's fair and just and equitable and addresses the historic injustice, the energy injustices that have been done to people, environmental justice concerns? How do you address all of that? And I'm going to show you some examples from the Princeton Net Zero America project, which we started before the last presidential election, specifically because we thought there might be a pregnant moment when information that this project produced would be valuable to help policymakers make good decisions. That's what I want to talk about now. So this is we released a report that made it into a lot of legislation that was pending before Congress, and we're currently doing a second volume, which is a gaps analysis, what remains to be done. I'm going to just say a couple of things about it. It's on federal actions over the next 10 years to put the US in a fair and equitable path to net zero in 2050. Those are the sectors. And what I wanted to say, because of the other position I'm in, the report's broadly compatible with policies proposed by the Biden administration, but it was developed independently. All right, so the Biden administration, that wasn't even an administration during most of this, had absolutely no input into what the final recommendations were. It's an important thing just to say. Now, the Princeton Net Zero America project, I started about 1.5 years before the election. And the idea was to do the most comprehensive planning exercise that had ever been done on how to get to net zero, what you had to build, and who would be the beneficiaries, who would bear the costs, so that you could walk into a congressperson's office and when they ask you what's in it for my people, you could actually show them, all right? And so the people who, we hired Jesse Jenkins at Princeton. If you don't know Jesse, you can see him on Twitter. He's probably the single most impressive energy expert of his generation. He's the person who's in front of everybody else. Chris Gregg is an Australian energy systems expert and former coal CEO. He's a businessman and government person from Australia. Eric Larson is a long time. And what I did was, after I got this started, is step back into the weeds. We also had all kinds of collaborators from Environmental Defense Fund, from the Nature Conservancy, from NRDC, from the big environmental organizations. And we had lots of participation from two of the biggest fossil fuel companies, ExxonMobil, who I normally wouldn't, well, I haven't ever worked with otherwise, and BP. And the reason for that is, well, you'll see the conclusions and you can decide for yourself whether or not you think they've influenced the conclusions. But by signing on, it means that they endorse their correctness, right? All right, so the idea here is that we wanted to analyze the cost of taking our current emissions and moving all the way to net zero in 2050 here. Blue are non-CO2 greenhouse gases, mostly N2O and methane. And green are land carbon sinks, mostly forestry. And what you can see is that the way the math works out, both in the US and globally, net zero means that non-CO2 greenhouse gas sources need to be roughly balanced by land sinks at mid-century. And the whole rest of the economy, power plants, cars, steel, everything else, that also independently needs to zero out, which means basically you have to get rid of all emissions from it, right? To zero that out if you're going to zero the others out the other way. And we had a whole bunch of different scenarios. There was a reference scenario, which you can think of as business as usual, but where we don't do this. There was the cheapest scenario, where you didn't put any restrictions on technologies that you were going to employ. You, for instance, allowed as much fossil and nuclear as was feasible to build if the economic optimization wanted to do it. There was one in which you said, no, somebody succeeds in limiting the rate of electrification because of political pressure. They want to keep internal combustion engines alive or something like that. Or it becomes out that consumers really balk at installing heat pumps in their house, that sort of thing. There was a high biomass scenario. The other scenarios don't admit large scale land use conversion. You can't, for instance, knock down the eastern deciduous forest, right? Where there would be significant pushback against. But in one, we said you can have a lot more biomass if you want it. In one, we had the fossil interests predominate, and we limit the rate at which renewables can be deployed to the maximum historic rate they have been deployed at. When this was done, that's now been passed, but we were limiting it to then historic rate. And then there's a 100% renewable case where you don't allow any fossil fuel use whatsoever. Okay, so those are the scenarios. The thing about the study that made it unusual is its granularity. And so the thing is actually done on a 6-kilometer grid everywhere in the country. It takes account of local zoning, local physical conditions, proximity to transport hubs, all kinds of stuff, and does the optimization on a 6-kilometer grid. That turns out to be hard to do. And it also turns out to be essential because politics is local, and what a person in Congress wants to know is what's in it for their people, right? So you have to have the spatial resolution to do that. This shows you the new transmission lines in dark blue, the wind farms in lighter blue, and you can't really see them probably from where you are, but the golden speckles are commercial solar facilities. And this is in 2030. If you look at 2050, it looks like that. You can see the great big build out off the coast in, New York State is planning on doing this massive build out off the coast and so on. And the transmission lines that go in are reconductoring and thickening the existing right-of-ways. We constrained this so that we didn't have to pass and get through the NIMBY pushback from new transmission lines all over the place, right? This is actually constrained. You could do this more cheaply if you could figure out a way to site new transmission. So if you zoom in on one place, I'm only going to do this once, and there is zoomed in on St. Louis, Missouri. So that's St. Louis, Missouri. That distance is 60 kilometers. These little squares show where we think the wind and solar are going to be. Those are the sites that would be best for wind and solar, zoned for wind and solar, exposure for wind and solar. And so that's the grain at which this thing exists, all right? And it does not just the time of the investment, but how much money it makes and all that kind of stuff. It does all that kind of estimation. This shows you a CO2 pipelines network. Turns out that even in a 100% renewable system, you need to be able to capture and move CO2 around, partially because cement and some other compounds produce it, and partially because you need to create some carbon sinks, and that requires that you get rid of some CO2 in one way or another. The size of the network you need is about the same, whether or not you allow fossil fuel to have carbon capture and storage, where the CO2 is distributed into reservoirs, or don't allow it. It's about the same size, a little bit bigger. It's like 0.7 versus 1.1 gigatons per year, like that. Okay, so that Princeton Net Zero America project was one of the many that informed this National Academy study. But to be honest, it had disproportionate influence because it has the most information in it. And so I want to talk about the lessons that we learned that came from the National Academy study. We reviewed everything that was written on this and did our own analyses. And the first is that deep decarbonization is surprisingly inexpensive. This is the fraction of energy system spending is a fraction of GDP, so that's 10% through time, starting in 1970, going out to 2050, here we are today. And what you can see is that every projection from the Department of Energy, these lines, the Princeton Net Zero America project, which is the purple, or the one previous comprehensive study by Halley et al., has the cost of the transition to net zero over the next 30 years be a smaller fraction of GDP than we've spent on energy over the last 30 years, all right? The main reason is that you avoid all of these oil price shocks caused, for example, by wars, okay, that leave you vulnerable and your economy vulnerable. It's one of the reasons. The other reason is this stuff is just cheaper. And this is true whether or not you're modeling a 100% renewable economy or the cheapest one that allows some fossil and nuclear elements. They're both cheaper than what we've done in the past. So anybody who tells you this is too expensive is either making the story up, they're using old data when wind and solar were 5 times more expensive, which was like 4 years ago, right? Or, well, those are making it up, mistaken or lying. That's the third one. Yeah, they're lying. Okay, in general, we think it's going to cost cumulatively to the economy about $200 billion for all of the 2020s to get on this. And $200 billion in Washington is not a lot of money. To give you an idea, the health benefit, as I'll show you in a minute, just from closing the coal plants during this period dwarfs that number. So it's really clear that especially over the next 10 years, embarking on this transmission is an economic winner on net. Doesn't mean there won't be winners and losers, but the net is a clear winner. The second is that, you often hear that this will revitalize US manufacturing and increase employment, but it turns out really to be true. If you do an exhaustive analysis, first of all, right now, there are only a few places where fossil fuel is found. And those places have booming fossil economies, right? Like the Gulf Coast in Texas. Appalachia isn't exactly booming, but at least it's an industry. And the sort of Rocky Mountain corridor where there's coal and gas and oil, Wyoming and North Dakota and so on. And those are the only places that actually produce the energy. Those are the communities that benefit. But photons and wind are everywhere. And so virtually every place in America would become an electricity producer. And that's a new industry for the 97% of communities that currently don't produce the energy to produce electricity. And so that's really what changes things. So this is a graph that's useful for a senator, at least. It's not so good for a member of the House. You got to go more granular than this. But what this is our employment analysis. Actually, Erin Mayfield, who was a postdoc on the project and has now started as an assistant professor at Dartmouth. And she put this together. And this shows different energy jobs. These are only the energy sector jobs. So these aren't the, the installers or the weatherizers of houses and all that stuff. This is just the hard stuff. This is the energy system itself. So fossil workers displaced by people who run wind and solar and other facilities. And if you look at this, you'll discover that coal, red here in Wyoming, see that coal is declining? That's Joe Manchin's state, right? Losing its coal economic base. Now you see Joe Manchin's state wins in the end, right? Primarily because of the growth in wind and solar. Turns out the topography of West Virginia is fantastic for wind and solar. The wind revenue alone produces by about 2035, $230,000 per annum of revenue to the state for each displaced coal worker, okay, turns out. Now, there's also some job loss, there's job loss in Louisiana, gains and then losses in Texas, losses in Oklahoma, losses like crazy in Wyoming. You see oil, gas, and coal are all taken at the shorts, North Dakota, but everywhere else in the country, it's up, 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 and up, okay? So this is, yeah, go ahead. Alaska? Yeah, this is the lower 48, sorry. Yeah. So actually we do have an Alaskan analysis, but I don't have a slide and I can't remember the full story. There's not very much Alaskan employment anymore in the North Slope, all right? All right, so, but they're high quality jobs, as you know, the ones that are there. So anyway, so this is the story. This is the story of many more winners than losers, but with a clear need to mitigate those that are going to lose their jobs and lose their communities and so on. So there's going to be a need for some proactive job creation. And the wild card is that we also have to create a net zero industrial base. We want to re-onshore a bunch of industry, and we have to build a net zero industrial system anyway. So why not put them in communities? Why not subsidize so that they're in communities that are going to lose some of these jobs? So there are all kinds of policies that can mitigate the losses that are concentrated geographically. The third lesson is that decarbonization policies must assure a fair and equitable transition with public participation in decision-making. This means you have to consult people and you have to ask them what they want and you have to listen. You have to listen to poor people, you have to listen to those that are historically disenfranchised, and you have to try to do what's right for the, and it's not just for normative reasons. If you don't do this, some group, this is the yellow vest movement in France, will become pissed off and they will stop it by protesting, okay? So you have to try to bring the public along. And the way to do that is to make sure that people are involved in the decision-making and that you try to distribute resources fairly. There are all kinds of disparities in our current energy system that we want to get rid of. There are a whole bunch of papers like this one. This is a particularly good recent one on air pollution exposure disparities across the US population and with income groups. And the important thing to know about the situation in general is that the energy transition helps American health, which is the biggest source of disparities with income and ethnicity in this business. So disproportionately, poor people and people of color are killed by air pollution, most of it from coal plants. These are the coal plants. These are the premature deaths. The redder it is, the worse it is. And under any net zero transition, by 2030, there just are none. All the deaths are gone with the coal plants. This is a business as usual. So the point is that although disparities remain, the net zero transition itself, by simply transitioning quickly, the disparities in deaths, which are arguably among the worst impacts, just go away, all right? Almost, because the total goes away. Fourth lesson is that deep decarbonization requires immediate action. This shows the lifetime in years of assets that we put on the ground, infrastructure we put on the ground, and a lot of these things are living 50 or 100 years, okay? And the reason why that's important is that we keep building long-lived emitting infrastructure. And if we keep doing it, then we have it as a legacy. And so the reason you have to act now is so you stop building it, all right? So you don't lock yourself in. Beyond that, the actions required in the first 10 years of this effort are essentially independent of the outcome, given that you're going to 100% renewable. One of the things that's complicated the debate about the energy bills before Congress is the debate between those on the green side, between those who want to have no fossil fuel at all and those that want to admit it, all right, that in a decarbonized form. And that debate turns out to be totally beside the point. So these are the different scenarios we have, from one that limits renewables artificially to the cheapest to 100% renewable. These are the different optimal sort of trajectories. Blue is onshore wind here. Gold is solar. The others down here are all fossil. I want you to zoom in on 2030, right, this decade. And the point is that at this point, above this point, it's all wind and solar. And you can see that everything except for artificially limiting uneconomically the growth of wind and solar, every single one of these things is the same. 100% renewable, and the cheapest one where you admit fossil and nukes, it's the same amount of wind and solar built during the next 10 years. So this is a debate we don't have to have now. And we'll find out late in the decade how much technology has dropped the cost of wind and solar, how much technology has dropped the cost of hydrogen and so on. And we can make an informed decision. But for now, let's put away the fight. Final lesson learned is that the expansion of RD&D is essential. Although you have almost everything, you certainly have everything you need to get started. There are a couple of sectors like aviation, marine transport, and others where we still need a fair amount of development. There are solutions everywhere, but some of them haven't been brought to industrial scale yet. Okay, so if you ever want to look at this report, you can look at its key findings and recommendations. The technology goals are all, and the quantitative targets that are attached to them are all built into the Build Back Better and other bills that have gone before Congress. There's widespread agreement among technical experts on what needs to be done technologically. The socioeconomic goals, how to support communities, businesses, and workers, promote equity and inclusions, strengthen the US economy, those are all over the place. And most of them, especially the environmental justice ones, are pretty much absent from the legislative action to date, and it's likely to remain so. So that's a ball it looks like that the nation is dropping, even if it gets its act together and passes a bill. If you ever want to look at this thing, you can look at it online, and it has this policy table with icons for the goals and different colors for how important they are. And it reconfigures itself on the fly if you want to learn about something. So if you want to figure out quickly how to build a non-emitting energy economy, just look this thing up, spend 15 minutes with the electronic reconfigurable itself tool, and you'll know what's going on, okay? All right, so I want to talk now about two issues on the way to closure. The first is that there is a fundamental dilemma in the current rhetoric between a just and a fair transition. That means giving all Americans, including historically marginalized groups, a say in what gets built within their communities. That's the way to do that. If we're going to treat people fairly, we have to give them all a say. But historically, this requires unprecedented consultation, and this takes more time. And the big problem with the energy transition is that it requires that we move faster to deploy infrastructure than we've ever moved before. So we're up against a hard place where the goals of diversity, equity, inclusion, and fairness are rubbed up against the need for a rapid technical deployment. And I don't know how to solve this, but it's something we're taking a look at. If you look now, only 11% of wind and solar projects make the completion. The rest are stopped mostly by pushback from the communities that are there. To reach the Biden administration's goal of 80% clean power by 2030, we would need to initiate 4 to 7 terawatts of electricity. And if you know anything about electricity, that's just not possible. So those numbers have to improve. We have to figure out a way to get more projects through faster while consulting. We have to figure out a way to have a consultative process that also leads to more rapid community acceptance. and no one knows. And so if you're going to work on anything and are a social scientist or an industrial psychologist or anything like that, this is a really important problem to work on. This just simply shows that the little speedometer bar here shows how fast we need to build stuff for the cheapest scenario, for the 100% renewable scenario. Here's back where the historical peak is. And you can just see that even for the cheapest scenario, we're up into scales of deployment that are really unprecedented. And if you try to build a 100% renewable scenario, you're up into a real inability to actually just deploy resources that quickly. And so this really is the fundamental constraint, and we have to figure out how to do better. We're currently engaged in a gap between the net zero trajectory and policies that have been implemented to date. And so what I want to do is focus on this. This comes out of Jesse's lab using tools that we all paid for as part of the Net Zero America project. BBBA here represents the Build Back Better bill, which failed before Congress primarily because the Dems couldn't get their act together to agree on it. A couple of senators objected, failed in the Senate, passed in the House. The IIJA is the bipartisan infrastructure bill you've talked about. That's the thing everybody touts as their progress on climate, all right? Now, I want you to look at this graph. Jesse's built this amazing tool that can take any build, do like a Princeton Net Zero America granular analysis on it super quick and figure out what it'll actually do. And so this is the historical rate of decarbonization of US greenhouse gas emissions in CO2 equivalent amounts. And you can see that we've been on this slow, steady decline as we've gone from coal to natural gas. And we've also then gone to now renewables and wind and solar, which are the leading growth areas in the energy industry. Now, this is then frozen policy, which you can see is basically just a straight line continuation. That's the policies before the last Congress. That includes New York State action and California action and all that sort of thing. And if you follow that trajectory down, we don't hit net zero till after 2100, which is too slow. Now, the bipartisan infrastructure bill that they all tout as a bipartisan compromise moves you from the orange to the purple. You see, that's almost not at all. The net zero trajectory we need to be on that gets us to net zero in 2050 is this light blue here. Build Back Better in two different guises, one in September and then the watered down one in November, are the yellow and green here. And you can see that they put you on a trajectory to decarbonize the economy. They meet the president's goals. They meet our national commitment that we signed as part of the COP26 agreement and so on. But the current policy leaves us not significantly displaced from doing nothing. And so my point here is that this is what you need to write your congressperson people about if you're going to write them about anything, if you care about global warming. Because right now, we're saying we're doing a lot and we aren't really doing anything. And there's a package of policies that have passed the House and that could pass the Senate before the midterm that will carry you down to the trajectory that we need to be on. It's the difference between not doing anything effective and doing essentially all of it, okay? It's that qualitative. Right now, the gap between policies that have passed and where we need to go is all of it. And it could be wiped out in one passage of one bill, all right? All right, I wanna just close with a few remarks about the Ukraine conflict. Obviously, the energy implications and the climate change implications of the Ukraine conflict aren't the locus of tragedy of the whole thing. You know, this thing was caused by a Russian invasion. People are suffering, and I don't want to belittle that in any way, shape, or form. Our hearts are with the Ukrainian people and understand that their suffering is the paramount concern that we all have. But nonetheless, people all the time ask me, well, what's this going? Doesn't this set back the energy transition? People have all kinds of views on it. And so I just want to give you mine, all right? Which, yeah, for what they're worth. Okay, the first one is, a lot of people worry because it means more short-term coal use in Europe. And that's probably true. all right? There'll probably be some more short-term coal use in Europe, particularly in Germany, and there'll be a little bump up in emissions because of it. So the lives of some coal plants are going to be extended. And that's because if you have to get rid of Ukrainian gas, it's easier to ship coal across a country than across the land than it is gas, especially if it's got to go across the ocean. There's definitely more emphasis in nuclear power in Europe, a lot more emphasis in nuclear power in Europe. This is a clear winning technology from this. You know, the Brits and everyone else are talking about really increasing their nuclear fleet so that their electrical system has some buffering from these kinds of shocks. Another positive, and that helps the greenhouse, right? Short-term coal use hurts the climate problem. More emphasis on nuclear in Europe, whether or not you like nuclear, it's a net zero source, so it helps the greenhouse problem. Reduced oil use everywhere. I don't know anybody who thinks that the war in the Ukraine, the invasion of the Ukraine, is going to decrease the pace of electrification of transport. Clearly, Europe is going to want to get off oil even faster. And it means more rapid electrification. And that percolates everywhere in the world. And so oil is a great big loser in all of this. There's no question about it. So there's going to be an increased rate of transport electrification. The wild card right now is gas, right? So the Ukraine, so if Europe gets its act together to stop imports of Russian gas, then they're temporarily in trouble. So Germany right now, you probably know, has a 2024 plan to get it off it altogether. But what if we did it more quickly? What would happen? Turns out the hit on Germany's economy isn't very big. I mean, it's easy for me to say. It's a couple of percent, 3% maybe for 1 year. So it's something that's feasible to contemplate, primarily because there are extensive plans within the US and the Gulf nations to liquefy the gas and ship it in these specialized transports to Europe to unload at the couple of facilities they have that can take it. And by scheduling it and sort of going on a wartime footing for loading and offloading, you can just about get it done. All right. It's not such a big deal in the short term because, of course, seasonal gas use is going way down as Europe warms up, but you've got to get their storage up before the next cold season. And so that's close to possible to do right now. Now, in the meantime, it's inevitable that they will build more LNG facilities everywhere, liquefied natural gas. Biden has committed to it. Europe is committing to it. Everybody's going to do it. And that's going to lock in more gas use. All right. And so normally I would say that's bad, but it's also going to increase the emphasis on carbon capture and storage from gas-fired power plants in Europe. All right. Because they really don't want the extra gas use. So there's going to be extra pressure to go for CCS. And on balance, it's hard for me, right? Because on the one hand, it is gas use. On the other hand, it is also true that the bigger your technology quiver is, the more tools you have in it, the more likely it is that we're going to get to net zero in time. And getting to net zero is a lot easier with a dispatchable source of electricity that's decarbonized, like gas with CCS, than it is without it. So I'm going to close you with what I think the end of the horse race is going to look like in 2050. I don't know how low global emissions will be, but I do have a better prediction on, I think, where the technology is going to be. Wind and solar are going to be the cheapest thing. You know, they're going to be so cheap, okay, right? And hydrogen for synfuels and industrial heat will also be cheap, probably a half to a quarter the cost that it is today, and fully competitive with natural gas or better. Efficiency is always going to be a big deal. You always can make places more energy efficient. Land-based negative emissions are still going to be a big deal. Direct air capture, machines that suck CO2 to the atmosphere are progressing rapidly, and I expect them to be a major player by 2050. Grid scale storage is going to be coming along. Photochemical fuels, artificial photosynthesis that uses photons to make fuels out of CO2 will be just coming on, and nuclear and gas with CCS will be kind of back in the pack, I think, outcompeted by some of these newer technologies that I think will pass them by. So that's all I have for you, and I'd be happy to take some questions.
impossible 1.5 degree target, but that's globally, right? So the US as a really rich nation.
Yeah, so if you look at the Biden administration's plan, right, it's faster, right, than that. It's the lion's share of it happens earlier, and then you have a longer tail at the end. And so the plan is to go to 80% decarbonized electricity, for example, in 2030. All right. And so you're right. I frankly think it's unlikely that we're going to globally get to net zero by 2050. But I also think that 2 degrees is well within our capability if we get our act together, both politically and technically. Yeah.
You mentioned how the transition to solar and wind energy would create jobs all over the United States. Do you see any feasible option for jobs that are currently in fossil fuel industries to be transferred over to those renewable counterparts?
You know, I think it's more likely. So one of the reasons that the Biden administration has been stressing hubs, so to build hydrogen production hubs, CCS hubs that'll take CO2 away and put it in an underground reservoir. They've been stressing most of the proposals, all of them have sort of job creation elements to them and displace. And so if you think about the skill set of a refinery worker, it transfers over into the net zero chemicals industry and a bunch of other industries more easily than it does into wind and solar. So I do think that the obvious thing to do is to build net zero industry with CO2 disposal facilities that where the best places to do it geologically are in former fossil fuel reservoirs anyway, right? And that's probably the best way to displace the fossil, right? To replace the fossil jobs. And you could do it proactively by simply incentivizing those industries in the locations where you want them to be.
Thank you.
Sure. Yes.
Hey, we've got 2 questions from the webinar. The very first is, we're in a state which said no to fracked gas. It's possible and probably fair to interpret this as a victory for climate advocates that would address the production and not the consumption side of New York contributions to climate change. It's simultaneously possible to view it as an effective use of politics and law to stop locally a controversial energy transition in the making. Do you think there are any lessons to take from this experience for the New York State or US energy transition future you've been discussing? Or is New York too much of an outlier to be relevant?
Well, so there's a lot there. All right. First of all, I know how fraught the controversy about hydrofracking and horizontal drilling has been in New York State. I also know that New York is blessed with options for reducing the emissions from its production of energy that surprisingly few states can match, in part because of the superabundance of availability of hydro. All right, you've got Niagara Falls, but you also have a deal with Quebec Hydro, which is like the largest energy storage facility in the world. And so New York's legislative plan is actually to get ahead of what the Biden administration's goals are. And it looks like they're going to be on track to do it. Now, the problem of the gap between consumption and production is real, okay? So everybody in New York is also buying goods that have emissions embedded in them. And this is the problem so the gap between production and consumption emissions is less a problem the bigger the geographic area. For instance, if you do this at the country scale, the difference between production and consumption emissions for the United States is like 10%. It's just not very much. It's because at the end of the day, we actually produce most of what we consume here. China, it's also not very big. You think of China as this giant export that is embedding all of our emissions in its products and selling them back to us. Yeah, it's true on the margin, but it's just not a big deal. On the other hand, if you look at something like Switzerland, where so much has to be imported because it's so small, then it really looks like a big fraction. So the smaller the political entity, the more it looks like the gap between consumption and production is a big deal, okay? And that's kind of all I want to say about that. 3 cheers for New York for having aggressive goals.
Thank you very much. And the second question was, Why will gas and CCS fall behind all of the other technologies? What are its particular downfalls that will make it less viable than others?
Yeah, so the reason I think, so there's a wild card. I should actually qualify that. Existing combined cycle gas, which uses a jet engine to run a generator and then collects the fire from the back of the jet engine and uses it to boil water, which spins a steam turbine, which runs another generator, which is super efficient then because you get 2 shots at it. And then where you capture the CO2 from the flue gas, compress it, move it into a pipe, and move it into storage is what we're talking about. And those last stages are actually kind of expensive. Now, there's a special thing called an alum cycle power plant that works differently. You can look it up online. There's a company called Net Power that produced a 50 megawatt one. I don't know, something like 6 or 7 years ago now. The thing works. They're building a bunch of full scale ones. And this is like a magic gas device where the CO2 was already captured and there's no smokestack at all. Nothing is emitted from an alum cycle power plant except for compressed CO2 and water that is potable, all right? And so if an alum cycle plant pans out, then everything I just said then that statement is almost certainly false. If an alum cycle plant doesn't pan out, then the extra complexity of capturing CO2 from flue gas and the energy that takes and the extra 35% energy penalty it takes to do it and all that, I just think it's going to, the competition from wind and solar is so intense, right? It's, the price point is so low, going down so fast. I think it's going to be tough, all right? Even though it's dispatchable, right? And if it exists, right? If there's any gas with carbon capture, it'll probably be large capacity, but used almost never. When there's big doldrums over the country and the wind power is way down, you might fire up a few of these things for a couple of days and then turn them off again for another year, like that. Yes, in the back.
Okay, can you hear me?
Yeah.
Okay. So with respect to the invasion of Ukraine, one of the results that you mentioned was decreased use of oil everywhere. But what we've seen in reality from the Biden administration is like one of the largest releases of oil from the Federal Reserves in history. So I was wondering if there is a way that you foresee getting beyond the political realities of electability and actually reducing oil usage.
Well, even though the Biden administration released oil from the Strategic Petroleum Reserve, most analyses calculate that the reduction in the price of gasoline was something like 10 to 25 cents a gallon. And it's the high price of gasoline that reduces its use, okay? And so they did a little bit just to soften things politically, but make no mistake, the price shock that came from the fact that only a few countries control most of the fossil reserves, and a lot of them aren't our friends, will continue. This game has been rigged for decades and decades and decades. And the only way to get off it is not to try to produce more of a product whose price is, after all, regulated globally and whose supply has to meet global demand. And thus, whenever there's a, whenever anybody pulls production out, there's a price shock. The only way to get off that is just to step off the merry-go-round, right?
Thank you.
Yeah.
So you mentioned that only 11% of solar and wind projects make it to completion. And this obviously has something to do with political indecisiveness and fossil fuel jobs. But does this also have something to do with environmental impact reports and the effect it has on the environment with the construction of these projects?
Yeah, I mean, I think that the concerns about wind and solar are real. My own prejudice is that it's mostly aesthetic. People can't stand the idea of the beautiful ridge that they've always looked at being just like covered by these monster machines, right? They don't like the transformation of the landscape. Certainly that was what the people in Cape Cod and the people on Nantucket were pushing back against, right? People didn't want their ocean views wrecked. And I understand that. That's why I think that the concerns against local people against these things are going to continue, right? Because, but one thing I will say to you is, I'll just give you a story. I'm going to give you some child rearing advice as a grandparent, okay? When our kids were little, my wife and I decided this was going to happen. And so we started to stop every time there was a big wind turbine. And there weren't many of them back there. And we'd stop and we'd get the little kids out and we'd say, isn't that beautiful? So beautiful. And we successfully brainwashed them, okay? And so now they actually do believe they're beautiful. I can still remember when they were in high school, we were biking in Denmark and I came across this half-timbered village. It was so quaint and beautiful, but there's this like 3 megawatt monstrosity going around. And I'm like, oh God. And my son turned to my daughter and said, isn't that beautiful? That's my advice. Yeah.
Do you want me to use mic or not? Can you hear me?
I can hear you, but I don't know if everybody else can. Yeah, I'll repeat the question after you ask it.
Okay, so there are other forms of renewable energy besides solar and wind. Say solar and wind, they have the cost reductions, they're using suspended. What about the other forms? Do you think there's a potential for the other forms to also have their cost reduced and expand their uses, or even replacing one of the or both of them?
So the question was about, I trumpeted wind and solar as renewable energy sources, and there are other technologies that could be used. There's tidal power, there's deep geothermal, there's a whole lot of other options that can be developed. And where do I think, are any of those likely to join wind and solar as real power players? I'm not really an expert on this. And if I knew, I wouldn't tell you I'd be a startup owner. That's what I would do. But my reading of it says that geothermal in all its guises, especially deep geothermal, could actually go someplace. All right, and that it scales, right, and could really go someplace. But the thing is that lithium-ion batteries in cars surprised everyone. The gas, the cheap natural gas surprised everyone. If you'd polled energy experts, is this Moore's law buy down of solar going to continue for another 30 years? I bet you every one of them would have said no. And just they were all wrong, right? We were just all wrong. So if you ask me what I expect the most, it's that I expect to be surprised by the developments in renewable technology.
What happens if you put a carbon price into this model for net zero? Does it fundamentally change some of the pathways, or do all the pathways adjust and it kind of just balances out? Like, do you have any insights on that?
Yeah. So the question is, what happens if you put a carbon price in this kind of an analysis, right? And so an analysis like this one takes an end goal, and the automaton says, I know what I have to build. And I know I have to stage it right, okay? And so I'm going to stage it appropriately to get everything done in time in the cheapest possible way. And that's a different path than if I just dumped a price on carbon and then the cheapest options are built first, and infrastructure that is large scale and expensive that you're not going to need until the carbon price is high, but whose time to build is long, like a pipelines network or an electrical grid, tends to be put off until later, you see? And so that's the difference, right? Especially the long-lived infrastructure planning. A carbon price together with prescient long-lived infrastructure build, supporting enabling infrastructure, that's a different matter, yeah.
Just one more question from the webinar. Are there any thoughts about constraints on materials for manufacturing the new energy infrastructure we're talking about?
Yeah, I mean, there's a lot written on that, right? And we've all heard the concerns about critical elements like nickel for some batteries that are right now not available from Russia and that sort of thing. We've all heard the concerns that rare earth elements are concentrated in a few countries like China, and the need to expand elsewhere. We've tried to look at fundamental material shortages and just have, it's not that it's impossible to get into a bind, it's just that it's all about price. When you say that some place is only available somewhere, what you're really saying is it's more expensive to produce somewhere else, all right? And so it's, when we tried to do a robustness analysis based on material shortages and haven't been able to come up with anything. We were really looking, when we did the Net Zero America project, for anything that was unfeasible. You can't deploy human capital that fast. You can't educate them that fast. You can't scale up aluminum production that fast. All that stuff is built in there. And we were unable to discover the kinds of impediments that we thought would be present. Yes. Yeah, so the question was, did I start in this field? And it should be obvious from the presentation that I did not, right? So I gave another seminar today for the biology group that was on the mathematics of plant coexistence, if you can believe it. It's the sort of thing that my Romanian grandmother would have said, Stefan, is that anything for a grown man to do? And so in my 40s, I decided that I was going to start paying back the social debt that I'd built up for spending all kinds of tax money on whatever interested me the most, and started to pay off the social debt by working on problems that confront humanity. And so I've kept them both alive, but I've just done more and more and more of them. And now I spend so much time in Washington consulting, sometimes at pretty high levels, and so it's paid off. And all of the investment I made as a basic scientist has paid dividends. Just the sort of clarity of analysis that you can bring to a problem really is best learned, I think, oftentimes in a basic research context. So you're absolutely right and astute. I didn't start in that business at all. What would I think about methane and what in carbon neutrality? I didn't hear the middle. Oh, from carbon neutrality? 50 votes in the United States Senate. That's it.
I have a question. So you seem optimistic that we can export some of this technology globally, which I think would require exporting jobs, money to developing countries. Are you optimistic that the U.S. Senate will support this? We won't be going for jobs in the U.S., but we might be going for jobs or development in Africa or India. What makes you so optimistic that we can do that?
Well, so I should be clear that however much I might support a great big increase in foreign investment and foreign aid, I don't expect it. And the Net Zero America analysis didn't assume any, okay? It's all about what's best in the United States for Americans. And we also didn't expect people to cut back much on their energy use because we didn't think they would, okay? And so this was for the current behavior patterns, right? And what we thought, yeah, so none of the analysis that I've presented, I think, what it does is it leads to intellectual property in the United States, which is then sold to other countries, right? In final products and licensing and that sort of thing. But no increase in aid, however much I think it might be warranted to do that. Yeah. Yeah, flying is, remember I said this little thing about R&D is essential because there are some sectors that are still hard to abate. I said kind of under my breath, aviation and marine shipping. Aviation's, look, aviation is something like 6% of emissions, right? It's not tiny, but it's not big either. The solutions for aviation, they basically fall into, let's call it four categories. One is that you could simply burn fossil in them. And for each gallon of aviation fuel that an airliner consumes, it is required to pull 10 kilograms of CO2 out of the atmosphere and put it in a geologic reservoir. If you do that, the net carbon impact is 0. And the goal for that direct air capture technology is $100 a ton. $100 a ton is exactly equivalent to $1 a gallon. So it's like adding $1 to fossil aviation fuel and you decarbonize all of aviation, okay? Second way to do it is with biofuels. Biofuels are already cost competitive, but the problem is that we're already short of land, all right? Short of land for biodiversity, food production, and energy crops, and sort of adding on aviation. Maybe you want to do it, but it's best if you can't. The third way to do it that is being explored is electricity for very short haulers. You've all seen the reports on battery powered planes that are good at 300 miles and that sort of thing. And for long haulers, going to electrolytic hydrogen. Pass a current with a membrane through water with renewable electricity and you make it hydrogen. You can burn hydrogen in a jet engine. And so there are 3 options here, all right? And I didn't mention it, it's a small number and we have a way to fix it. Nothing is commercial scale yet, because that's because nobody's decided to go all the way on it.
Yeah, I guess similar to her question, where does like the food system fall in this equation? Like you think you need to shift more towards like.
Yeah, so you'll notice that I said that, you know, I like to think about this problem as decoupleable, because people oftentimes think that land carbon sinks are letting oil companies off the hook or something like that. And what they don't realize is that because of the relatively large residual N2O and methane emissions, almost all of them from agriculture after you've cleaned up the fossil sources, to offset those, you need just about all the land sink capacity of carbon that we actually have, which means that the land would zero itself out. And, you know, it's a pretty simple theorem to prove that then that means everything else must also be 0 if their sum is 0, right? And so I think it's useful to talk about all the industrial stuff about getting to 0, to simply sidestep the inevitable proposal that why don't we just offset the fossil use, right? All right, with trees or something, all right? So what about the food system? So anything you can do to reduce food, methane, and ammonia is good then, right? And it also is possible that the food system, that agricultural practices could be used to store extra soil, CO2 in agricultural soils and still help rebuild their health. We have people in this room who are working on that right now. Beyond that, if humanity were fundamentally to change its diet, then, and not need so much pasturage and not need so much grain for cattle feed, then you would both reduce methane and you would free up a whole bunch of land that could be used for another purpose, like biofuels, feedstocks for aviation, or carbon sinks by planting trees on them. And so I do think human diets are a big deal. If I had to choose what category they're the biggest deal in, is that right now with the food, water, biodiversity, and climate problems, land use is a zero-sum game globally. We need every square meter of the Earth's surface purposed to a particular problem, and we have to use it all. If we can get cattle out of people's diets, all right, we free a big chunk of land that we could do something with, all right? So it's no longer a zero-sum game. So this to me is a really important thing. I hope maybe artificial meats can do it. It's been really difficult, as you no doubt know, to change people's diets.